Suresh, and Suresh has been a longtime friend and a colleague of mine. And I'm so sort of happy to present to you. And I think there are certain advantages of COVID, right, in terms of people bringing together virtually, and that sort of brings a tremendous opportunity for people to meet. Also, I want to acknowledge a number of my school friends who I invited to join the lecture as well. So I hope that all of you will find this lecture interesting and hopefully something that you can sort of bring it to your robotics experiences. So as Sunil mentioned, I'm at Columbia University. I'm a professor, but also my degree is in mechanical engineering, which I obtained from IIT Kanpur about 1984. And so by training, I'm a mechanical engineer. But it so happened during the my journey, my work, I got a chance to meet clinicians, a lot of physical therapists, and basically a lot of robotics was being used for industries to see how you can sort of manufacture things well. And then we asked the question, is there a way for us to take these robotics technologies to human health? And it was sort of a tremendous journey for me. I learned a lot, and it seems that more and more to me that robotics can actually be used as a very versatile tool for movements and training of various kinds of functional movements. So that is what I'm going to talk to you about and walk you through some of those. So a little bit about my university. We are in heart of New York City. I'm in Manhattan. And just for those who do not know Columbia University, it's a very old university. And we have had the distinction of having up to 84 Columbian alumni, faculty, adjunct faculty who have received a Nobel Prize at some point in their careers. Our university is also proud to have 8 Nobel laureates on its current faculty. Also, I want to say that in the US News and World Reports, Columbia ranks 3rd among US institutions. So it's a really kind of a very thriving and a dynamic environment for people to sort of work as well as sort of create new things. So let me kind of dive right into my topic. And we know that we are all going through this global health challenge. Okay, and one of the things that I show on the left of the screen is a rapid growth of population and a lot of older people in our society. And we know that our people who are 60 years and older, I mean, there's more and more presence of that demographic in our society, and that's all over the world in any continent. On the right, I have some information from the World Health Organization. From the WHO, there are some statistics out there that a lot of people today lose work. So if I think of, let's say, female or male, some of the things that prominently sort of go in there are back pain, people fall down a lot, kind of Alzheimer's disease or heart diseases. So these are all things that are there prevalent in our society at the moment. On the bottom here, I show you that the World Health Organization estimates that there are about 1 billion people worldwide who would need some sort of an assistive technology, right? The simplest form of assistive technology could be your eyeglasses. So if I think of this way, I took my eyeglass off, I can't see anything, right? I put this on, and I have now an assistive device which allows me to kind of look at and see things. But what I'll be talking more with you today are people who have got sort of mobility needs, people who are on wheelchairs or who need crutches, or who have got, let's say, a lost limb. And there are many such people who could actually benefit by robotics as a technology to help them in their daily life. So a little bit about what I do in my lab. And this is to look at various impairments, and some of these could be neural in nature, right? People have a stroke, or they've got a Parkinson disease, they've got sort of some kind of a brain disease that doesn't sort of allow them to make the movements or understand and so forth. So we look at how robotics can be used, and here you can see the robots to have very different forms. So for example, robots can help you to walk, or it could sort of allow you to sort of correct your back. Many people have scoliosis. Or if you think about, let's say, we have a head drop, or people are not able to walk well, or let's say people are getting older, we want to understand what is their cognitive health. So really kind of robots can allow you to address many of these issues that are prevalent in our society. And we'll kind of discuss a little bit more why robotics in the coming slides. But if you think about the human body, right, the brain is sort of your kind of the intelligence, like the computer in your body, right? And if you think the spinal cord as the highway, right, which essentially takes information from the brain to your muscles, or maybe some of the sensory information that you see or your touch and things like that sort of goes back to the brain. And basically that sort of is the closed loop between your computation, which is at the brain, as well as the decision making, and then eventually kind of execution of that. So what is very interesting here is that the brain, of course, it has the capacity to learn. And whether you are a 3-month-old baby, or you are 65 years or 85 years old, right, brain has the capacity to learn, right? And what has been shown is that through training, you can always sort of have improve your functions. So what we think of robotics as something we call it as a training wheel on a bicycle, right? So think of, let's say, a 5-year-old who's learning to bike, right? You first time you put him on the bike, the child will fall down. So what the moms and dads will do is they will put a training wheel on the bicycle, right? So now what it does, it really protects them from falling and exercise, and they can sort of have a more natural experience. And as they develop the skill, essentially they don't have to use the training wheels anymore, right? So this is sort of the same analogy that we use here, is that if somebody has a stroke or somebody has a cerebral palsy and they've got an impaired function, how could you use the machine as a way to sort of help them reacquire that function that they have lost, right? And you would use this machine during the training process, but once they have trained, they don't have to use that crutch anymore, or you would sort of throw away the robot, and then they should be kind of, hopefully they are doing better in terms of what they have lost. So in our lab, we have a lot of different projects, and I have listed a few of them out here. And I would not have time to sort of talk about every one of them, but I would have a few of them that I'll sort of talk to you about today, and especially the top half out there, which is sort of all relating to balance, walking, or maybe your posture, and things of that nature. And of course, I mean, there's a lot more information on our website, and you can sort of go in and find more information, or you send me information and I would sort of give you more information as needed. So let's kind of go in a little bit about why robotics, right? So if you have a problem with human health, you go to a doctor, right? And the doctor will sort of give you certain medicines and hope that you are able to sort of improve by the medicine. Now, what we are thinking about here is not just the kind of cell level issues, but what we're looking at are movements in your daily life, right? Walking, balance, sort of standing, or maybe your upper body control, your reaching, and so forth. And if you injure, let's say, your arms, right, or you have a fall, or you sort of injure your legs, often you would go to a physical therapist. And what the physical therapist would do is sort of apply forces and movements, or they'll manipulate or they'll modulate your movements in a way that you become you have some temporary relief, and over time you sort of improve upon it. And what we try to do is we want to use the robotics in the same way to retrain movements, right, by modulating forces similar to how physical therapists would do. Now, so if you put a machine on the human body, right, there are lots of challenges over there. How do you design it so that the machine is sort of transparent on the human body? And also, how does the sort of machine interact with the human in a way that you can sort of relearn your lost function? And so what we do is we kind of touch upon a lot of principles of human learning or motor learning, and we see how we can incorporate that within the principles of the robot. And we'll go through some of that in my talk, and so that way you can see some of that. Now, another interesting thing here is that robots inherently are sensing devices, right? So you can actually quantify the progress. And so often if you injure your leg, you sort of go to your doctor and he says, okay, you are doing better today, right? But the question is, what does better mean, right? Can we quantify it? And so the robotics has sensors, and that is a natural way of quantifying information about the human body and see how it is changing over a period of time. So the progression of that can also be assessed. Now, also the robotics can be sort of a fun way to ask some basic science questions or intervention question, right? What would the human body do if I use the robot in this way or the other way, right? Would it sort of help you to do things? And that is again a very exciting part, because nobody has ever done those kinds of things before. And so that gives you many fundamental basic science questions to ask. So we call those as what if questions, and I'm going to lead you through many of those what if questions in my talk today. So let us kind of see a very kind of fun application of a robot, right? So a question that we asked ourselves many years ago, almost like 15 years ago, if I take a 6-month-old baby, right, can the baby learn to drive a robot? Right, and you may be wondering, why do I sort of care about a baby kind of driving a robot, right? And what you saw here are videos of 2 babies, and they are kind of sitting on a little chair, a typical baby chair, but they are connected to a mobile robot, and they have got a little joystick, and with the joystick they can actually sort of create movements, right? And so the question is, why do I want these children to drive a robot? And what is interesting here is that self-generated mobility, right? The ability of the children to be able to be mobile by themselves is very important for their development, right? In terms of spatial awareness, where they are in the environment, right? Their visual system sort of develops very quickly at an early age, right? So the vision, your posture, all of that is sort of very interlinked in terms of being able to move around. And we know that there are many children who are born with various kinds of impairments. So of course the cerebral palsy is one of them, but you have spinal bifida or many other issues where they are not able to sort of move by themselves. And the question here is, can you sort of use the robot as a way to sort of facilitate them to move around in an environment? So these are some experiments that we did here. We took a 6-month-old baby, put him on a chair, and gave them a joystick. And of course, the first time they see a joystick, they really don't know what to do. But on the other hand, if you are able to work with them, train them over a period of time, what you will see here, that they will actually be able to learn to drive a robot, right? So these are 3-month or 6-month-old babies, right? They are not able to crawl, they're not able to walk. But you can actually teach them to drive this robot and come and get toys or get some food and so forth. And also, if you think about social interaction, right? I mean, social interaction is a very important phase for the development of the child. And in this case, we actually did a study with up to 50 children and these are all in the range of 3 months to a year old. And what we could show here is that in about maybe 6 or 7 sessions of training, you could sort of teach these children to be able to drive around and do lots of interesting things. And part of our hypothesis was that if these children can be mobile, then they can actually, even though they may be physically disabled for whatever medical reason, they may still be able to use that mobility and obtain various other aspects of their development. And many of these children would eventually sort of develop, they have to be kind of wheelchair bound for a later part of their life. And the question here was that how do we use a mobile robot to actually move around in an environment? So this is one of our daycare centers, and this is a child who has a cerebral palsy, and we are sort of teaching this child to actually navigate around in this environment. And what he has here is a joystick, which is called a forceful joystick. And in this joystick, essentially, if he is pushing his joystick in a direction that is not in the right direction, the child actually experiences a force on his hand. And through that force interaction, the child eventually learns how to kind of guide himself and drive around in an environment. And that this technology sort of enabled us to take these mobile robots into the homes of these children. I don't have some of those studies here in my talk today, but we had a whole series of experiments that we conducted here, where this technology could actually be used in their home environment, and we try to ascertain how these kinds of mobility would affect their social development and so forth. So what you see here on the right is 2 groups of children. We call it the control group and the training group. So the training group actually is the force feedback joystick, which was sort of giving information about how he should kind of move the joystick in order to navigate, while the control group was using a typical kind of gaming joystick. And what you see here is the children with the force field, they were able to kind of train to have more smooth patterns and go to the goal, just like what you saw in the video, while the children who were not, they were not able to sort of do this as skillfully. So the point here that I want to make is that even children who are much younger, in the range of say 3 to 12 months, there is a lot that you can do with robotics to help them in terms of their development, both physical as well as kind of social development. So let me sort of move on to another topic. So what I have here in my talk is 4 or 5 kind of vignettes that we'll talk about. And of course, we could go to any one of these in a lot more detail, but to keep the general overview nature of the talk, I'm sort of giving you sort of short vignettes of this. So let us sort of come to the next topic here, which is gait rehabilitation after stroke. So as many of you know, stroke is an incidence where the blood supply to the brain is temporarily lost, and as a result of it, certain cells in your brain die, and those cells may have been responsible for kind of doing various kinds of coordinating various kinds of movements. So, for example, in the United States, we have about the population, we have about 300 million people, and in our society, in US, we have about 4 million survivors, stroke survivors. So you can think of, let's say, 1 in 300 people who may actually be kind of have a stroke. And many of these people would survive, but survivors of stroke have one-sided weakness, which we call as hemiparesis. And many of them actually have sort of asymmetric gait patterns. They're not able to walk very well. They walk with a foot drop, or maybe they are kind of dragging their toes. And also they are very susceptible to balance losses and falls and things like that. So, so here on the video here, let me kind of play this video one more time. What you see here are some of the patients with stroke undergoing physical therapy. And there are these 3 physical therapists who are sort of trying to help relearn the movements. And some of them are actually kind of providing kind of physical support to them at the upper body level. And some of them are sort of helping you sort of regain the movement pattern in terms of how the legs sort of move to in your walking. So our goal was this is a video from about maybe 15 years ago, when we sort of got into to see how we can replicate these same ideas with a robotic exoskeleton. And this exoskeleton we named as ALEX, which is an acronym for Active Leg Exoskeleton. So what you see here is a person walking on a treadmill. His right leg is the weak side, which is not able to walk well. And so he's been attached to this machine, which is anthropomorphically designed to fit this individual. And then what this machine will do is apply forces on the foot in a way that they can attain a more regular gait pattern. And of course, I mean, the question is, how do you kind of create these forces and so forth? So there's a lot of detail out there, but on a high level, what we're trying to do is we are trying to mimic the same training that you saw in this video here, and be able to sort of do the same training with the machine. So the question was, of course, I mean, this was a very long project for us, almost went in for 10 years or so. And we kind of developed a lot of different kinds of exoskeletons. And I've got one here, it is a second version of ALEX, we call it ALEX 2, which we used in a lot of human studies. And what you see here is a study with stroke patients. And in the video on the top, this is the first time the patient was introduced to this device, and you can see he's walking with a very small confidence. He walks very slowly. He does not have as much sort of movement on the leg, which is his weak leg. In this case, this is the left side of his leg, or the left leg. And what you saw on the bottom here is the video of the same person who underwent a multi-session training with this particular device. So I'll tell you a little bit more about the multi-session training. And so this training was over 15 sessions over a 3-month period, and each training was roughly about 45 minutes or so. And what this training was to look at his foot pattern. And here I have a little schematic of the foot pattern. So somebody with a stroke, maybe he started out with this black template, which is a small template. That means he doesn't have as much movement of the leg. And the goal here is, how do we sort of stretch that template over a period of time to this dash green template, which would be sort of corresponding to a more healthy gait. So of course, these training studies are very long and laborious. In this case, you can see actually two physical therapists who are clinicians who were sort of involved in the study with these stroke patients. And of course, we had the engineering support in terms of the design of these machines and everything, which we all built in-house. And basically it was sort of improved over a period of time and so forth. So this is a study that we had with n equal to 9, basically means that there were 9 subjects who underwent this study. And so the study was for 3 months. And then we had a 6-month follow-up. That means once the study was completed, they went home, and we asked them to sort of keep on practicing walking outside in their home and in the community. And then what we did is we kind of brought them back at 6 months later on to see what kind of changes happen as a result of this our training. And we have some very interesting results here, which is sort of described in this plot here. There are 3 graphs. One of them is the yellow, the blue, and the gray. So this is the group data. So it's not an individual subject's data, but from these 9 subjects who were in our study. And what I plot here is the self-selected speed of walking. But this walking speed is not on the treadmill, but is an overground walking, right? So it's something that how you would walk in a community or in your home. And what you see here is that on an average, these subjects were walking at 0.6 miles per hour, right? Just to kind of, or 0.6 meters per second. And just to put this in a perspective of, let's say you and I kind of walking, this would be about 1/3 of the speed of kind of a healthy individual who has not had a stroke. Now this blue template basically says here that at the end of this 3-month of training, they were actually walking faster as a group. And there was a significant difference in their walking speed before the training and right after training. But what is even more interesting is that 6 months later on, when they came back, right, and in those 6 months, they were really not asked to do anything from our study perspective, right? They actually kept on increasing their speed of walking. That means they were walking faster at their homes in their community, even though they had done this study sort of, say, 3 months earlier. right? And that was a good scientific result, because what it says here, that this kind of robotic training can actually make a difference in your walking balance and your speed, and that you can sustain over a long period of time through these kinds of technologies. So, so we learned a lot from this experience, and of course the question was for us engineers are what are some of the challenges in this technology? How can I sort of make it better? How can we sort of bring these kinds of technologies to their home environment so that they have a better access and so forth? And so those were some of the engineering questions, and of course, I mean, there are questions about how do you implement those ideas in these patients as well. So that led us to sort of think about that these machines are fairly heavy and bulky. So in fact, the Alex machine weighed about 20 kilograms, right? And to put that in perspective, let's say you and I are sort of in the range of 60 to 70 kilograms, right? So which means that this device had a weight of, let's say, 20-25% of the body weight, which of course is okay to do in a lab. But if you have to sort of bring it to community or in their home, that is sort of not so easy to do. So one of the challenges that we sort of pose on ourselves is, how do I make this machine from 20 kilograms to 2 kilograms, right? And we sort of completely redesigned our technology. And in this case, we designed this exoskeleton. We call this as a cable-driven leg exoskeleton, or it's a C-Alex as opposed to the Alex. And in this case, the weight of this machine is about sort of 2 to 3 kilograms. And the disruptive technology that we used here was instead of metal links that were connected between the various body segments, we have 3D printed cuffs that the person is using at the pelvis, the thighs, and the shank. And in between, there are these wires. And the wires are actually like your bicycle kind of brake wires, right? And we call them as a Bowden cable. And so those these lines that you see are the lines for the Bowden cable. And then there's a motor that is sort of sitting on the frame, and that is transmitting these forces. And what we're able to show is that through this 2 kilogram technology, you can achieve something similar to what you achieved in our previous studies. And here is a study that we did later on with stroke patients, just like you saw a previous study. This was not a multi-session training study, but it was a single session study to show the feasibility of the idea. We just kind of published this recently in the journal to show that you can actually get similar effects even with stroke patients. And here is a stroke patient walking with this assistance of the C-Alex. And you have some plots out here to show how you can still control the forces from the wires in a way that could affect the gait, and you can sort of retrain gait of these individuals. So this sort of allows you to take this technology outside the laboratory into the home environment or in a community center and so forth. And that way you are able to sort of bring this to a broader kind of spectrum of people. So let me kind of move on a little bit more here. We have, in our lab, we look at a lot of technologies that is designed for to improve balance and gait. And I would sort of like you to sort of look at this picture of this mother holding this baby, right? And as a baby is learning to walk, right, the mother would not necessarily take the leg and sort of move it in a pattern. But on the other hand, the mother would actually kind of hold the child at the pelvis level, right? And as the child is not able to sustain the balance and they may be able to fall and so forth, essentially you can modulate that, and the child would eventually learn to develop the walking gait over a period of time. So that sort of motivated us to sort of think of a device which is, we call it a pelvic device, and we call it a tethered pelvic assistive. I call it TPAD. That's an acronym that we use. But basically what it does is mimics what the mother is doing to the baby to modulate the pelvic forces. And the way we do this here, instead of the hand of the mother, we have a little belt. And on this belt, we have many wires, and these wires are connected to the motors. And essentially, you can tension these wires or apply forces in a way that could mimic what the mother is doing. And I'll show you how we have used this idea in a number of different studies later on by arranging these wires in different ways that you see out here. This is a video of somebody kind of using this device, and you can see here it's a very transparent device. The person can walk naturally, and he has the belt, the same belt that you see in the schematic here. And while they're walking, you can also kind of look at a lot of physiological data, both in terms of their movements as well as very muscle activities or how they apply forces on the feet and so forth. While in real time, you can actually control the tension in the wires to apply a force as you want to. So I'm going to show you a few implementations of this. And one of our application is a lot of older people, of course, fall down. They have a poor balance. And the question is, can we actually train them to improve their balance using this kind of technology? And what you're seeing in this video here on the left, as the person is walking, you're actually pulling the person sort of in the forward-backward direction, right? It's something like you are on a train and the train stops and you kind of get a little jolt. And you have to sort of really recover from this jolt. On this right video, the person is walking while you pull the person from the side using these wires. And you can sort of really control the sort of the pulse duration, how much force you want to apply, how much, in what direction is being applied. And so you can really kind of play around with this in a kind of a closed environment. And we actually have a motion capture system that will actually allow you to sort of capture the movements and use that information to do real-time control and so forth. So let me show you one of the studies that we did, and this is for patients with Parkinson disease. And here is some data on the subjects themselves. These are PD group is the Parkinson group, HC is the healthy control group. So the patients who were enrolled in this study were about 65 years old, and they had been diagnosed with Parkinson's disease. And what we really did is we call it a perturbation-based training. And in this perturbation-based training, as they are walking, essentially you pull them in different directions, and these come in randomly. And we want to know how that improves the balance of these individuals. So let me see if I can play this video here, and let me know if you can hear this video or not.
Sunil, the voice is not audible, but we can see
Oh, not audible?
Yeah, usually the voice in the videos will not be audible. Yeah.
Oh, okay. So Suresh, so this is the maximum video I have on it.
Okay. Yeah.
Can you see the video at all?
Video we can see, but not the audio in the video.
Okay. So I will let the video run, and then maybe I'll tell a little bit more.
Yeah, sure.
So Suresh mentioned that you cannot hear the audio in the video. So basically, it's the same device that I showed you earlier on, but in this case, this was used with Parkinson patients, and we had a single session where they were given up to about 85 perturbations in different directions, and then we look at their gait and balance sort of before and after. And what we actually found is, and you can see these the two plots on the right side. This is the on the y-axis something called the anterior-posterior margin of stability. And the way to think of margin of stability is while you're walking, you have your center of mass and you have base of support. Okay, and closer you are at the boundary of the base of support, you are essentially unbalanced. And what you see here is that the healthy control, of course, has a better margin of stability compared to the Parkinson group. But what was interesting here is in this particular plot on the right side, which is called the baseline, early post-training and late post-training. And we have the same y-axis, the variable, the margin of stability. And what we actually show is that the healthy subjects actually increase their margin of stability in the same way as Parkinson's disease patients. And the reason why this is sort of very important is for many of the Parkinson patients, improving the balance is very hard to do with the typical drug that is given for Parkinson's disease patients, which is the levodopa drug, but doesn't sort of affect the balance of these individuals. So they need something else, and we feel that this could be a good training approach for them. Okay, so I'm going to sort of move on to the another study here that we did again with a different group here. And these are children who have got cerebral palsy. So these are cerebral palsy children. And they have something called a crouch gait, right? As you see this child walking, you see that his knees are not straight as you and I would walk with. And these are typical kind of issues with patients with cerebral palsy. Just to put a little bit of information, in the United States, 1 in 300 children is diagnosed with a cerebral palsy. And about 1/3 of these children cannot walk without assistance. And depending on what is the level of CP, of course, different children have the CP manifests in different ways. But gait and balance is sort of an important issue for these children. And what you saw in this video are these children who have got flexed hips, knees and ankles, and they walk slowly. It's a very energy intensive gait. And also it affects the joints because you're walking in a very awkward way. And as a result, your forces that are applied in the joints are different than the normal gait. And over time, I mean, they would actually develop knee osteoarthritis and things like that because of this unusual kind of load on their knees. So typically, these children with crouch gait, they are retaught to walk, okay, using something called a weight suspended treadmill training. And the way to think about it is that when you're walking, you have your body mass or body weight. And suspension basically means that you take away a part of the weight. So essentially, I'm kind of lifting them up or taking away a part of the body weight. And these are called body weight suspension treadmill training. But clinically, it has been found that this doesn't work very well. When the children are being suspended, they walk well. But on the other hand, when you put them on the ground, they kind of regain this unusual walking pattern. So what we thought is, why not sort of do something differently? Instead of doing a body weight suspension, why not do a body weight augmentation? So what you see here is a little schematic. This child is walking, but what we do with these wires, we can apply a downward force. And in this case, we take a 10% body weight external force that we apply on the child while he's doing the walking. And the goal here is that during walking, you have to really kind of pull your body up against these external forces, and that will help you to improve or strengthen your extensor muscles in your leg. And that is sort of the hypothesis in this study. So I'm going to show you the same video here of this child. Okay, so this is on the top, you saw the child walking sort of before training, and you can see the crouch gait. But after training, you can see here, he kind of walks a lot more straighter. His knees are not as bent as anymore. And of course, this is something that happened over a multiple training session. And in this case, we had 5 children who underwent this kind of training. And this is just one of the videos of one of the child in here. On the left side, you can see the training being given to these children. You can see those wires very well. But on the left side is the child when he come in the first session of training, and by the end of the training, he's kind of walking with a longer step length, a better sort of gait and things like that. And that's what you help the child to improve his balance during walking. On this bottom right, you can see this, we call it the force. So when you walk, you have a heel strike and then you have a toe off, right? So these are 2 points in the cycle where you actually apply a lot of force on the treadmill. So typically, healthy subjects actually develop 2 peaks, one when they do a heel strike and the one when they do toe off. Okay, and these children with cerebral palsy with the crouch gait, they actually don't have those peaks, and their peaks are really kind of diffused over time, and that's the reason they're not able to sort of get that sharp, crisp force that they generate with the ground to sort of propel them. But these children, by the end of the training, they actually were then developing all these crisp gaits, and that translated in terms of better walking. And so some of this work appeared in Science Robotics that gives more details into it. So I'm going to sort of move on to another area, again, for children with cerebral palsy, but many of these children have got very poor trunk control. So for example, on the left side here, you see a child. He's just not able to sort of sit straight. Because he just doesn't have enough balance and strength in the upper body to be able to sit straight. And so part of our goal was to see how we can sort of help these children develop a better trunk control. And this is sort of a contraption that we developed. We call it TRUST, which is an acronym for Trunk Support Trainer. And essentially what it is similar to the TPAD device here, but in this case, you have a belt which you are wearing, and you can move it across the trunk, where you lose kind of lose the control on your trunk, and then essentially we have you kind of work to re-strengthen or kind of develop your trunk control by making various kinds of challenging you to do various kinds of movements. But in this case, the machine sort of creates a little donut-like force field around you, right? So if you were to sort of lean too far away, you won't be able to sort of come back to your neutral position. But with this external donut-like force, you are able to sort of be able to brought back to your neutral configuration. And the goal here is to expand that donut force or the ring around you without actually needing a lot of that donut force. So from a training perspective, what you do is you create this donut, but you would modulate the force that you get assistance from the donut in a way that eventually you become sort of self-sufficient and you develop your own strength over a period of time. So I'm going to sort of show you a video of one of the studies, and of course these are kind of large studies. These are multi-session training studies. We had 5 children with cerebral palsy who actually went in the study. Here you can actually see a child, and she had a very poor trunk control, as you can see. And we have a physical therapist who's kind of working with this child, and the child is wearing this TRUST device. And essentially what the physical therapist is sort of getting the child is to make different movements with the trunk. And in this case, the ball or the head is just a surrogate for making those kinds of movements. And during this training, so this is a video of the same child after the 2 weeks of training, and you can see here the child now has a lot better control in terms of their posture and the balance, and they actually are able to lean forward a lot further up, and they're able to sort of come back to their neutral position after being sort of displaced from there. And so this is a phenomenal pilot result that we got, and we are going to expand on this study with 75 children with cerebral palsy, and this is a new study that has been just approved from the National Institute of Health to look at a randomized clinical trial where we would have, let's say, conventional training methodology and this robotic method to see what sort of differences are there and what, yeah, this is a second child, just to show that you can really have a variety of kids with different sort of impairment, but they all would eventually be able to benefit from this kind of technology. So we have taken this further into another group of individuals, and in this case, these are patients with severe spinal cord injury. And we know that spinal cord injury is a phenomenon worldwide. There are about 40 to 80 cases per million worldwide. And of course, this is an injury to your backbone. You may have an accident, your car accident, you fell off from horse riding or whatsoever. So in the United States, we have 12,400 new cases of SCI or spinal cord injury. And as we kind of talked a little bit earlier on, your spinal cord is sort of your communication highway between your brain and your muscles. And also it kind of takes information to the brain as well as sort of takes the information from the brain to command your muscles. So you can have, due to the injury, you can have a sensory loss or you can have a motor function loss, right? So sensory loss is what is going to the brain, and you may have disruptions in terms of what information sort of goes to the brain. And in the motor function loss, I mean, the brain sends information, but it cannot sort of get it to the muscles. And so the spinal cord injured patients, they are described on the ASIA scale, which is A through E, A being the extreme case, the most severe cases where people would not have sensory as well as a motor capacity, while E would be sort of more milder. And the question here is, how do you take a patient who has got a spinal cord injury and be able to sort of rehabilitate them to be able to sort of stand and kind of later on do their activities of daily living. And so, of course, I mean, that's a big challenge for our research community. And this is some funding, or this is a research that is supported by the Spinal Cord Injury Research Board. And what I show you here on the left is a picture of somebody with a spinal cord injury, and they are sort of helping the person to be able to independently stand. And so the standing is an important part of the recovery process for the spinal cord injured patient. And what you see here is that the patient with severe injury, he is not able to sort of balance himself because he can fall down at any level. He doesn't have a control on the knees, the ankles, the hips, or the trunk. So they really can collapse in many different ways. And that's why we have these three therapists who are supporting the individual, one at the pelvis level, two at the knee level, and the person is actually kind of holding this bar, and that will sort of give him support. And in this case, I mean, the expectation is that the person is able to hold and exert forces by the hand, even though he's not able to sort of control the lower half of his body. So what we really did is we extended this idea of this keypad, which you saw, whether the pelvis device, the truss that you saw as the trunk device. And so this is a combination of these two devices in a single system. And we call it a robust, which is an acronym for Robotic Upright Stand Trainer. And in this case, what you can do is, so what you see here is the person kind of standing on some force plates. So there are two force plates underneath the legs. And also there's a motion capture system that sort of looks at the kinematics of the individual. And in real time, you can apply forces either at the trunk or at the pelvis. And these forces can be really designed in different ways. You can perturb. So for example, you're standing and you can basically be pushed around different ways. Or maybe you can think of, let's say somebody is sort of falling down and the machine would sort of catch them. And so you can either use that as a perturbative system or you can use it as a way to kind of assistive system. And we want to sort of use a combination of this perturbation and assistance in a way that we can improve the function of the body. So there's a recent study that we have published on some of the capabilities of this particular stand trainer, which is in a recent paper that appeared in the IEEE Transactions. And what we have done is we have actually created two of these systems. And one of these systems is actually now, one of them is now at Columbia Medical Center, other one is at the University of Louisville in Kentucky, and with our collaborator, Susan Harkema. And this is just a picture of how the system looks in their facility. And of course, we designed for them because that's a hospital with spinal cord injured patient. And that's where we are actually doing a very aggressive recruiting to understand some of the scientific studies with them. So on this little picture here, we show you a kind of a visual feedback to the individual, and this you can think of, let's say, the circle center would be the neutral position of your pelvic center. And this blue one, let's say, is your current position. So that way you can get a visual representation of how your pelvis is relative to your neutral. So that way it sort of helps the patient sort of come back to the neutral. And also in some of their studies, they also put an epidural stimulator. So these are some things that you can actually, so this is like a pacemaker, but now you put it on the spine. And you can electrically put signals in them. And that has been considered to be a breakthrough in terms of kind of neuromodulation for these patients with spinal cord injury. So we are coupling that neuromodulation that they are very kind of famous in their laboratory with some of our rehab work to see if we can use a couple system to help these individuals. So I've got a few videos of some, okay, so here is one of the patients. He is actually a 52-year male. He has got an injury in his cervical portion of the spine called C4. And he has got an AISB, which really means that he has got a partial sensory loss and a complete sort of motor loss. And we are sort of using our device in different ways. So on the left, you kind of saw the previous video was a stable standing by themselves. And here the patient is actually trying to initiate anterior posterior trunk motion. And of course, this is a multi-session training studies, kind of lots of repetition. This is another subject here. This is a female subject with also C4 injury. And in this case, she's also kind of holding the handrail, which is a conventional. So we're trying to sort of compare conventional training with holding handrails versus this T-pad or this robust training, which is essentially kind of supporting you at the trunk and the pelvis. And some of the high points here are that now with training with robust, we don't really need as many physical therapists. That means you can provide them a better sort of scientific training procedures, as well as you would have a lesser need for individuals to kind of work with these patients. So in this video here, what we're doing is we're actually doing a postural perturbations. So in this case, the wires are actually applying forces, and the subject have to come back to neutral by themselves. So this is an ongoing study for us right now. We are in the 5th year of a 5-year project to show some of the initial feasibility of this ideas with robust. So I'm going to sort of move on to the last topic, which is to look at patients who have got a poor head drop or poor head control. And a lot of people actually have head drop. And here you can see a video of a lady who's not able to sort of keep her head against gravity. And of course, I mean, you can relate back to many patients with ALS. For example, if you remember Stephen Hawking when he was on his wheelchair, right? I mean, he would not have any control on his muscles, and the only thing that would be able to move would be his eyes. And the question here is, how do you create these devices that can actually help people to be able to control their head and later on eyes? And so here's a robotic neck brace that we have developed in our laboratory. It is all sort of designed from the scratch in our laboratory. And this could be used as in a variety of ways as a measurement device, as an assistive device. And I'm going to show you later on a video of a patient with ALS who actually, where we're kind of looking at applying these two. So here is a patient who has an ALS. And ALS stands for amyotrophic lateral sclerosis. And in this disease, what happens is that all of your muscles progressively die, and what you're left with is only kind of your eye movement. So here is a patient with ALS, and he's got a head drop. Of course, he doesn't have a good control on his head muscles or neck muscles. And what we're trying to do is see if this robotic neck brace can actually help the person make these movements. So he's seeing an avatar on the screen, which is guiding him to do the movements of the head neck. And on the left, he's just not able to do it because he just doesn't have any control on his head neck. But on the right, you see that he can independently do these movements with the active assistance of the brace. And this is also a part of our ongoing project where we are recruiting a lot of ALS patients within the study. We also have some eye gaze control, which is sort of interfaced with the neck brace, and that sort of allows this patient to kind of provide information with their visually and make these movements. So I've got a few more slides, and I think it's a very, very important topic that I'm very interested right now. We know that at least in the United States right now, there are 3 million people, old people who fall every year, and about 800,000 of these fallers among these 3 million, they need to be hospitalized, and that means they sustain an injury that was large enough that they actually have to be hospitalized. And the question is, why do people sort of fall? And of course, the fall is a very multidimensional kind of issues. But what we look here in our study is to see how your vision, which is what you see with your eyes, proprioception is what you sort of feel, either through touch or through your sensors or kind of stretch receptors on your muscles, and vestibular basically in your ears, right? In your ears, you have got a little kind of ear canals tell you the orientation of your body. And the question is, if I look at these different sensory signals and how do these sort of affect movement and balance during walking? And here I've got a little a flow diagram here, which is sort of representative of balance during walking. And what you see here, the sensory system sort of plays a big role because the sensory system allows you to sort of understand what the environment is and how you can sort of plan your movements in that environment. And so what we try to do is we try to kind of manipulate the sensory aspects, and that's something kind of very easy to do with robotics or with some of these wearable technologies. And through the manipulation of the sensors, we want to understand how that affects your balance and walking. And I'll show you a few sort of videos of some of these things here. So this is an old lady who's kind of walking on a walkway, on a hallway, and she's wearing a virtual reality system. So these are VR glasses. But in the VR glasses, her visual field is not static, but actually is oscillating. And so on the right-hand side, you can actually see what she's seeing in her VR form. And basically, we have programmed the VR to show kind of an oscillating visual field. And we want to understand how that oscillation affects her walking. So she's actually walking on this instrumented mat, and that gets information about the step length, step width, and many of the other gait and balance parameters. And we want to understand how does perturbation on the visual field affect her walking. And in this particular study, we were trying to compare how young people and old people kind of get affected by these kind of perturbations. And there is a recent paper that just came out in Scientific Reports, which basically says, so I'm going to sort of walk you through some of the pictures here. So SL is the step length, right? So when you're walking, you're taking many steps, and we're looking at the average of these steps. And this kind of a shadow here is for young people, and these are the dark one actually for old people. And in this study, we had 20 old individuals of roughly of the 65 plus age group. And what you see here is that young people and the old people actually respond to these perturbations differently. And that's not surprising, because we know that as we grow older, as disturbances come to our visual signals, we get affected by a lot more. And so of course, I mean, the older people walk with a smaller step length. They have a larger step width, right? So larger step width basically means that you walk with broader steps, and that sort of gives you a bigger base of support. That means allows you to be more stable. Right? So as you can see her walking, I mean, she's taking kind of wider steps a little bit from her from her natural one. So we compare the reality, the virtual reality, as well as kind of oscillating the visual field in different ways. And what we also find is that the older people adapt to these sensory stimulations in different ways that younger people. This is another video where we're trying to see if there is a proprioceptive feedback. In this case, there's a light touch. So the person actually, while walking, they can keep their hands on this robot, and the robot would actually just follow them as they're walking. And the robot doesn't actually provide them physical support, but this is a very light touch support. Some is kind of less than a few hundred grams or so. But what we've actually shown is that through this light touch, individuals are able to walk with more balanced gait. And that's sort of very important for us because many of our older people, they have gait unbalances and they can benefit by these kinds of technology. So this is like a new version of a cane, right? We know that canes are conventionally used for many years to give you the sense of support of the ground. And in this case, this light touch could be another technology that could help them to walk better. So with this, I want to sort of come to a close here. We are holding the IEEE Bio-Robotics Conference. This is sort of a biannual conference every 2 years. We are holding it in New York City. It's the end of November, early December. Earlier, we wanted to have a physical conference where we could sort of have people come to New York City, but in light of pandemic, we have to make this as a virtual conference. But that also brings an opportunity because this is a virtual conference that is free and open to all. And in this particular conference, we have really about 200 technical papers from all over the world, and really all the kind of the leaders of the field are really present at the conference. So I'm the conference chair for this meeting, and I invite you all to attend. So there is really no cost. You can sort of go and Google on the website and find out more details if you want to kind of join in. So of course, I mean, all of these cannot be done with a very energetic group of people who work with me. Many PhD students, postdoctoral research, a lot of medical professionals, a lot of MD students, and so we've got a really very dynamic team which can look at so many different aspects of the problem. Also, I'm going to sort of acknowledge my funding agencies: the National Science Foundation, the National Institute of Health, the Spinal Cord Injury Research Board, the ALS Association, and we have a great set of people. On the left, I'm kind of just showing you a study that we do with. We do a lot of animal studies as well, because the animals sort of actually can provide you with models of many of these injuries. In this case, these are spinal cord injury, and here the animal is actually his hands are connected to this robot, and we're trying to see how we can sort of understand the recovery of this animal. In this case, is kind of doing the feeding task with his arms, and we use some of these principles in the design of our robots. So I'm going to sort of stop here and happy to take any questions that you may have.
Thank you very much, Professor Sunil. It was a wonderful talk. We have a few questions that have been typed in the chat window. Are you able to see the questions, or would you like me to read them out for you?
I'll appreciate if you can read, then that way I can sort of focus on more answering the question. Yeah. And we have a lot of time for question and answer, so please feel free to, and happy to sort of answer these.
So there is a student from IIT Tirupati who's asking, his question is about the recent presentation by Neuralink. In their demonstration, they presented a BCI chip which performed gait prediction in pigs. Even though the engineering part is impressive, I want to know if the neuroscience part is ready to build such devices that use feedback from brain to restore the gait of patients.
Yeah, so okay, this is thank you for this question, and this is a very interesting question. And of course, many of these medical issues they have got many facets to them. I'm sort of looking at how robotics and integrating robotics within their learning process. But these brain machine systems, of course, are also gaining a lot of popularity, and you can look at the brain signals. In fact, we have done some studies in our laboratory where we look at the activity or in the different parts of the brain as you kind of using the robotics as a way to kind of learn. And so how the networks in your brain sort of get connected over time. We have done some preliminary study, but we are not an expert into this. But there are so many different groups who are looking at rehabilitation from other perspectives, and the brain and some of these chips are wonderful ways of kind of adding into the repertoire of these things. Yeah, so I'm not sure whether I answered your question the way you wanted to, but yeah, but this is a very promising technology.
We have another question from Tushar Deshpande. Why is EEG-based corrective feedback for the motion not more prominent than his method, especially for stroke paralysis surviving patients? That way, even if the neural response is not correct, but the mapped EEG signal is going correctly, we can easily get correct output. And also, this would drastically reduce the technology training time to a single session rather than multiple sessions.
Yeah, so it's again a very interesting question. I mean, EEG, it gives you sort of spatial information about your kind of ensemble of your neurons, how they're doing. Now, often, I mean, what EEG did, I mean, so EEG is spatial information, right? And you also sort of augment that to the temporal information that comes out from other sensory systems that you can do from blood flow and others. So really, I would say that not one solution is the right solution, but it is the integration of many solutions. And in this case, the EEG combined with, let's say, the robotics would again be a very potential, a very I mean, has got a lot of potential in the future. In fact, there are many laboratories where they're trying to see how you can merge these different principles that are there in biomechanics and the electrophysiology to be able to sort of integrate the two together. So, of course, I mean, EEGs are very small signal. They are microamps, right? So a lot of noise can sort of get affected, right? And also, one doesn't really know. I mean, even though you're kind of recording from a site, but what you're really recording is sort of a mapping from many of the neurons up to that point. So there are kind of issues with the EEG signal, but again, it's kind of emerging as an important topic.
What are the various sensors and actuators that were used in the system? How was the system validated for different cases? And how to assess the selected system parameters are the correct ones?
Right. So many of our devices, of course, can use the so the robotics essentially would have motors, encoders, force-torque sensors. These are at the machine level. At the human level, you have the kinematics, which is sort of measured by a motion capture system. You have the neurophysiology, which is from the various muscles, maybe various kinds of force interaction that you have between your treadmill and the body. So really, you are not looking at. I mean, you are looking at the sensors that are there within your human body, as well as the sensors there on the machine. And really, you have to think about this as a collective system of machine and the human, right? And what you're really doing is you're acting upon those signals and providing commands to your machine, because that's the only command that you can provide. And you're hoping that by modulating the commands on the machine, you're also able to over time, modulate the command coming out from the human. So of course, it's a complex process. And you can use the various level of assessments of the sensors. So if you, I mean, it's easier for you to kind of validate some of your sensors on the machine but not as easy to kind of validate on the human body.
Professor Anand Suresh also has a question. How much benefit can one gain if neuroscience angle is explored in your studies? For example, EEG to fMRI or other imaging could uncover more insights.
Yes. So I think so. We work a lot with neuroscientists, and you're completely right. The neuroscience has to be sort of integrated along with the engineering, and as you said, the EEG and the fMRI, they are kind of really, fMRI is sort of the temporal kind of information, gives you temporal information, EEG gives you the spatial information, and by that sort of you can make a map of what's happening at the brain level. Because often when you do these kinds of training studies, the way you sort of keep the brain involved in the activity is central to the human learning. So a lot of studies have actually shown that if you build a machine and put on the human, and the machine moves the human in different patterns, it's not going to sort of help you to learn the movement. Because the learning theory requires you that you involve the person in that learning process. So yes, you're right. I think the two angles have to be sort of brought in, both from the neuroscience and the engineering.
There was another question where they're asking what are the different cost elements involved in replicating the systems in India?
Well, the cost itself of these devices is not very much, if you think about it. The cost is typically, I think we're getting some disturbance there. Yeah. So the cost itself is not of the main components. So any of these systems would sort of can be easily fabricated by, let's say, for a few $1,000s. So I would not say that the cost is a big issue, and they can be easily replicated in India or wherever.
Thank you very much, Professor Sunil, for very patiently
I have
answering
another
all
question.
the
Can I
questions.
ask?
Oh, yes, please. Yes.
Yes.
Sunil, this is Suresh. Great talk. It's a lot of impactful work. I actually think that you have turned the problem inside out. By that, what I mean is you have used cables very effectively, very ingeniously. So inside the body, we have muscles and tendons and all these things are cables. You put them outside, and the brain is inside. Now you put outside to your processing. Is that a good analogy? And I'm really amazed the way you have used cables.
Yes, so I think part of the motivation was that the cables are very lightweight, right? So if you think about sort of a meter of cable, right, it's sort of it's a few grams that you add on the human body. So a lot of the technology in rehabilitation suffers from the fact that you're using very heavy devices and equipment, right? And that makes it. I mean, first of all, you change the mass distribution within the body, right? So if I'm weighing 70 kilograms and I'm wearing this device which is 20 kilograms, and now you train this 90 kilogram system, right? How much that training will sort of eventually translate to the human body? So that has been a sort of a challenge, and so I think the cables are definitely a good direction in the field of rehabilitation robotics, and sort of lot of people all over the world now are using cable systems in many different ways, and that I feel is the future of rehabilitation robotics.
Yeah. And a lighter note, did your inspiration come from the puppets, or?
Yes, I mean, so the first, I mean, earlier I used to kind of explain these cable systems as really puppets, right? So these are kind of puppeteering in some way, and of course, you don't want to use 2 cable per joint because that makes it too many cables. So what we actually found out is that you can come up with a minimum set of cables for a certain degree of freedom, right? So you can have an n degree of freedom system from a movement perspective, and you can show that you need a minimum of n+1 wires to actually route it in some sort of optimal fashion. But of course, in most designs, we go more than n+1 because we want some redundancy to be able to sort of apply those forces that we want to.
Okay, Professor Sunil, I have one question.
Yes, Pradeep.
Actually, when there is some ailment there, and that is because of the nervous system. Now, do you have to map out the nervous system so as to find out the ailment at which place is it, and how to cope with that one, to have additional aided robotics using there. So in how to use that robotics, which would come afterwards, when it has all the nervous system, that has to be mapped out first, and then application of these robotics there being used to solve the problem such with the. So that is the external aid that is being added to that one. So do you have to map out first the nervous system, and then you apply your mechanics and your engineering devices there?
Yeah. So Pradeep, thank you for this question. It's a great question. So you can think of a disease at a cell level, right? So cells, there's something happening in your at the cellular level or microbiology level, and then some of the manifestation of that disease sort of comes out in your functional movements, right? So what we are doing, we are doing things at the functional movement level and see how you can sort of help at that level. Whether whether that help that you do at the function level, whether it translates back into the microbiological level, we don't know. And of course, I mean, so what would be nice to actually look at the effect of what you are doing at the biologic or at the biomechanical level into the cellular level, right? And that mapping. So what we really need to do is sort of simultaneously look at both of these, right? But this is a field that is sort of emerging. This is sort of a developing field, and right now it is not developed to a point where you're kind of simultaneously monitoring the two sides of the problem. So right now, what I was sort of giving you the side of the problem at the biomechanical level, but simultaneously we have to work with clinicians and doctors who can simultaneously sort of also monitor at that level, so that we can document what is happening at both levels. So even though most of what I presented to you was happening at the biomechanical level. And that sort of goes back to the comment that Suresh made, that from the neuroscience level, I mean, you have to also document things. And so this sort of gives us a natural topic for neuroscientists and engineers to kind of work together so that they can address this common problem.
If there aren't any further questions, then I'd like to thank the speaker, Professor Sunil, for a wonderful talk.
Revati ma'am.
Yes, please.
Yeah, Professor Atre sir, would you like to ask anything? I have muted your speaker twice.
Yeah, I was just going to say
Yeah, apologies for muting it. Yeah.
practical utility of the kind of work Professor Agrawal is doing is amazing. And the quantum work seems to be, I think it's time that in India also, as I said, you point out something with societal implications. And I think I must congratulate him on a very lucid what they are doing. And glad to see there were no equations which I couldn't. That's good. Congratulations, Dr. Agrawal. Excellent work.
Yeah, thank you, Dr. Atre, for these kind remarks. Yeah, thank you. Yeah, this is a really kind of a field. I mean, we engineers are often sort of looked upon as people who are sort of impacting the future, say 30 years down the road or 50 years down the road. We make a bridge or we make buildings and houses and things like that, right? But the question is that we can also sort of impact on a very short-term basis people in our community, right? And I think this is a direction that robotics is right now taking. And I think with all the technology, the way it's going, that is entirely possible to do that. And I think we as a sort of group should sort of make that happen and see how we can impact people and their lives.
Hello, I have a question. Am I audible?
Yes.
Yes, sir.
Okay. Hey, very fascinating talk. I have a question more on the sort of an inverse problem. So now with all these people with cerebral palsy or Parkinson's, the more they go through some of these focused trainings, do you see any sort of remapping in the brain? Is there something like a healing that is going on which can probably make it more recovery faster and better?
I think it's a great question. So yes, I think the mapping the brain is sort of an important part of it, right? So even though I'm not doing myself, but I think I want collaborators or neuroscientists to sort of help me do that. And that's where the opportunity for these larger collaborations where you have these multidisciplinary teams where people with different expertise can sort of work on the same problem. So not only are we able to look at it from a functional movement point of view, but at the brain perspective or how the signals are being sort of transferred across the different sort of organs within the body. So it's really a complex problem, and I think we could sort of really benefit by people from different disciplines kind of working together on these topics.
Yeah, absolutely. Thank you.
And I think this is a good time to end. Thank you very much. Thanks a lot to our speaker for Professor Sunil for giving a wonderful talk, and thanks for all of you for participating and contributing so much to the talk. Our next session, our next talk is going to be by Professor Ashok Jhunjhunwala on October 21st, and will be talking about what does it take for India to use only renewable energy resources. So hope to see all of you there. Thank you very much. Good night.
Well, thank you all for inviting me. I'm really pleased that I could share my share information with you all.
Thank you, Sunil, for your fascinating, this talk. It was very interesting and fascinating. Thank you.